Hello my dear students, I hope all of you are doing well. This is the second lecture of the unit Solutions and Colligative Properties. In this unit we are going to discuss about the solubility of gases in a liquid, the Henry's law, the validity and the applicability of the Henry's law. In addition to this, we will also solve few numerical problems. Okay. In our previous class we have discussed about the vapor pressure, the Raoult's law and the ideal solutions. The link for that class is given in the description box. So without any further delay, let us start today's class. Before starting the today's lecture, let us first discuss about what is the solubility. The solubility of a gas in a liquid at a given temperature is defined as the amount of the gas dissolved in a given amount of the solvent at that temperature. And basically there are three factors on which the solubility of a gas in a liquid depends. So we are going to discuss the factors in details. The three important factors on which the solubility of a gas in a liquid depends are nature of the gas and the solvent, temperature and pressure. So we will discuss about these factors in detail. So let us start with the first factor, nature of the gas and solvent. So generally easily liquefied gases are more soluble in common solvents. For example, carbon dioxide gas is soluble in water. So some gases which are capable of forming ions in aqueous solutions are much more soluble in water. As for example, ammonia is soluble in water, which is capable of forming ions, mainly ammonium ion and hydroxide ions with water. But ammonia is not soluble in benzene because it is not able to form ions with benzene. Okay. The second factor is the temperature. So at a constant pressure, the solubility of gas decreases with rise in temperature. To understand this, we can consider the dissolution of a gas in a liquid is a process which is exothermic. Okay, so therefore, according to Le Chatelier's principle, decrease in temperature favors the solubility of a gas in liquid. Okay, so therefore we can say that the solubility of a gas it decreases with rise in temperature, or solubility increases with decrease in temperature. Okay, a practical example of this is that we generally store the soft drinks in refrigerators so that low temperature is maintained and carbon dioxide gas is easily soluble in soft drinks. Okay, now the third factor is the effect of pressure. At a given temperature, the solubility of a gas increases directly with pressure. Now let us discuss the effect of pressure on the solubility of a gas in a liquid in details. To understand this, let us consider that a gas is taken with a liquid in a container which is fitted with a movable piston as shown in the figure. Now if we increase pressure on the system by pressing the piston, the volume decreases. As a result, the number of gaseous molecules per unit volume increases. Secondly, this causes a stronger interaction between the gas molecules with the solvent molecules, as a result of which stronger intermolecular forces exist between the gas molecules with the molecules of the solvent, and hence the solubility of the gas in the liquid increases. The effect of pressure on the solubility of a gas in a liquid can be best explained with the help of Henry's law. This law states that the mass of a gas dissolved per unit volume of a solvent is proportional to the pressure of the gas in equilibrium with the solution at constant temperature. Consider if m is the mass of a gas dissolved per unit volume of a solvent and P is the pressure of the gas in equilibrium with the solution, then at constant temperature, according to Henry's law, m is directly proportional to P, or we can write m is equal to K into P, where K is a constant which is known as the Henry's law constant. If the Henry's law is valid, then the graph obtained by plotting the solubility of the gas against the equilibrium pressure of the gas at constant temperature should be a straight line, which we will discuss later. Now, it has been found that the most gases obey Henry's law provided that number 1, the pressure is not too high, number 2, the temperature is not too low, and number 3, the gas is not highly soluble and does not dissolve or enter into chemical combination with the solvent. So these 3 are the validity of the Henry's law. Okay. Now Henry's law can also be stated as follows: the pressure of a gas over a solution in which the gas is dissolved is directly proportional to the mole fraction of the gas dissolved in the solution. Mathematically, we can write P2 is equal to K into X2, where the subscript 2 refers to the gaseous solute and X2 is the mole fraction of the solute. So here this also the constant K is known as the Henry's law constant, and the value of K can be obtained by plotting P2 by X2 versus X2 and extrapolating the straight line to X2 is equal to 0. Now let us discuss the plots. We have pressure P is equal to Henry's law constant K into mole fraction X. Give it equation number 1. Comparing this equation 1 with the equation of straight line y equal to mx plus c, we get c is equal to 0 and m is equal to k. So if we plot partial pressure against mole fraction, then we will get a straight line passing through the origin like this. So the slope of this straight line is given by slope equal to k. Okay, again on taking logarithm in equation 1, we get log of p equal to log of k plus log of x. Now if we plot log p against log x, then we will get a straight line like this, right? The Henry's law constant values in torr for some gases at 25 degrees centigrade are shown in this table. Since k is equal to p by x, so lower the value of x, higher is the value of k. That means the lower is the value of the solubility of the gas, higher is the value of k, or in other way around we can say that with decrease in the value of the Henry's law constant k, the solubility of the gas in the liquid increases. So therefore if we plot the solubility of a different gases against pressure, we get a plot like this. Here in this table you can see that the value of k of oxygen gas is lower than that of nitrogen gas. That means oxygen is more soluble than nitrogen gas. So the straight line of oxygen is shifted towards the y-axis, right? Now let us solve a numerical problem. The problem is the Henry's law constant for hydrogen gas in water is 5.34 into 10 to the power 7 torr. Calculate the solubility of this gas at 25 degrees centigrade if its partial pressure over the solution is 760 torr. Assume that the density of the solution is the same as the density of the solvent. So to solve this problem, suppose x2 is equal to n2 divided by n1 plus n2, where x2 and n2 be the mole fraction on the number of moles of H2 and n1 be the number of moles of water. We assume that number of mole of the gas hydrogen n2 is very less than that of water. So therefore we can write x2 is approximately equal to n2 by n1. Now the number of moles in 1 decimeter cube of water, that is n1 equal to weight by molar mass, which is equal to 1 decimeter cube by m, which is equal to 1000 ml divided by 18 gram per mole. This implies N1 equal to 1000 gram divided by 18 gram per mole, since the density of water is assumed to be 1 gram per ml. So therefore 1000 ml equal to 1000 gram. This implies N1 equal to 55.5 mole. Now from Henry's law we have P2 equal to K into X2. So this implies X2 is equal to P2 by K. Now X2 is equal to N2 by N1 and equal to P2 by K. This implies N2 divided by substituting the value of N1 equal to 55.5, which is equal to P2 by K. So this implies N2 is equal to P2 by K whole into 55.5. Now substituting the value of P2 and K, we get N2 equal to 760 into 55.5 whole into 5.34 into 10 to the power 7. On simplifying we get N2 is equal to 8 into 10 to the power minus 4 mole per decimeter cube. Hence the solubility of hydrogen gas in water is 8 into 10 to the power minus 4 mole per decimeter cube. So in this way we can solve this problem. Now the application of Henry's law. First one is in packing of soda cans. So soda water bottles are always packed under high pressure to increase the solubility of carbon dioxide gas. As we know, according to Henry's law, the solubility of gas increases with increase in pressure. The second application is in the deep sea diving. So generally nitrogen is more soluble than helium gas in our blood. In deep sea the pressure is higher than at the surface of water. So when the diver goes deep into the sea, nitrogen gas becomes soluble in blood along with oxygen and other gases. But when the diver tries to come rapidly towards the surface of the water, pressure decreases and dissolved nitrogen gas comes back from blood and make bubbles in veins. So such medical condition is called bends, where the blood veins becomes swallowed and we feel pain. Okay, so hence the divers use oxygen gas diluted with helium, and generally in the oxygen cylinders along with 56.2% nitrogen and 32.1% oxygen gas, 11.7% helium gas is mixed. Okay, so that the mole fraction of the nitrogen gas decreases, and as a result of which the solubility of the nitrogen gas also decreases. Clear? The third application is at higher altitudes. At higher heights the fractional weight of oxygen is not as much as that at the ground level. This stimulates low concentration of oxygen in blood and tissues of individuals living at high heights or climbers. Low blood oxygen causes climbers to feel feeble and not able to think plainly, indications of a condition known as anoxia. Due to lower solubility of oxygen gas in our bloods at higher altitudes, some people may feel unconsciousness or vomiting. Such conditions are collectively known as anoxia. Now can we consider the Raoult's law become a special case of Henry's law? So let us check this. According to Raoult's law, we know P is equal to P naught into X. Give it equation number 1, where P is the partial pressure, X is the mole fraction, and P naught is the vapor pressure of the pure component. Again, according to Henry's law, P is equal to Kh into X or K into X. Give it equation number 2, where P is the partial pressure, X is the mole fraction, and Kh or K is the proportionality constant known as the Henry's law constant. Comparing both the equations, we get that partial pressures of the volatile component or gas is directly proportional to its mole fraction in solution. Hence Raoult's law is a special case of Henry's law when the Henry's law constant Kh becomes equal to the partial pressure of the pure component P naught. The Henry's law constant is approximately equal to the vapor pressure only for the ideal mixtures, which does not exist. Still, Closely related substances like benzene and toluene can form a close to an ideal mixture where this case is applicable. Now let us again see the applicability of Raoult's law and the Henry's law together. In several cases of solution of gases in liquids, it can be shown that if Henry's law applies to the solute, then Raoult's law applies to the solvent. To show this, we may make use of Gibbs-Duhem-Margulis equation from thermodynamics, according to which d log of P1 divided by d log of x1 minus d log of P2 divided by d log of x2 is equal to 0. Give it equation number 1, where x1 and x2 are the mole fractions and P1 and P2 are the vapor pressures of the solvent and the solute respectively. Now let us assume that the solute obeys Henry's law. Then we can write x2 is equal to k dash into P2. On taking logarithms on both sides, we get log of x2 is equal to log of k dash plus log of P2. Now differentiating equation 2, we get d log of x2 is equal to 0 plus d log of P2. Since Henry's law is a constant, so derivative of log of k dash is equal to 0. So give it equation number 3. This implies we can write d log of P2 divided by d log of x2 is equal to 1. So hence from equation 1 and 4, it follows that d log of P1 divided by d log of x1 is equal to 1. Give it equation number 5. Integrating equation 5 and taking anti-logarithms, we get P1 is equal to k into x1. So give it equation number 6. So from equation 6 we get P1 is equal to k into x1. Here in this equation, if x1 is equal to 1, that is if we have the pure solvent, P1 will become P1 naught, the vapor pressure of the pure solvent. Hence the value of the constant k in equation 6 is equal to P1 naught. The equation 6 may therefore be written as P1 equal to x1 into P1 naught. Give it equation number 7. The equation 7 is the expression of Raoult's law of the solvent. Thus we see that if any solution the solute obeys Henry's law within a certain range of concentration, then the solvent obeys Raoult's law over the same range of concentration. Here I am giving you some problems as homework. Problem 1 and 2, these are two multiple choice questions. The third one is also a multiple choice question, and the fourth one is a numerical problem. So solve these problems and post the answers of these 4 problems in the comment box. I will be waiting for the feedbacks from you. So this is all about for today. See you in next week. Till then, enjoy your learning.